Okay, so let's continue our discussion related to filters. So in today's lecture, we'll look at filters which are made up of inductors and capacitors, and we'll see how resonance enables us to build filters with very high selectivity. So let's start with a practical problem of, let's say, we want to wirelessly transmit speech signal. So we know our speech signal lies anywhere between 20 hertz to a few tens of kilohertz. And although the speech signal is complicated, but we have seen earlier that it can be decomposed into sinusoids. So let's, for the sake of discussion, suppose we have a signal of a frequency of 1 kilohertz. And we would like to transmit it wirelessly. Now the problem is that when I take the signal, I feed it into an antenna, then the antenna size for efficient radiation is related to the wavelength and wavelength of the electromagnetic wave. And if my frequency is very low, then the wavelength becomes very high, and the antennas become impractical. And so the point is that low frequency signals like this are very difficult to transmit wirelessly. On the other hand, if I want to transmit a 1 kilohertz, let's say, so this is like our speech signal, if we want to transmit it from A to B, so direct wireless transmission is difficult, if not impossible. Okay, so we have a problem if we want to transmit it wirelessly. On the other hand, if I take a signal like 450 kilohertz, now 450 kilohertz signal is relatively easier to transmit. If I take a 450 kilohertz and I want to transmit from A to B, let's say several tens or hundreds of kilometers away, I can wirelessly transmit this particular signal, 450 kilohertz. So 1 kilohertz signal cannot be transmitted wirelessly, while 450 kilohertz signal can be transmitted wirelessly. So how do we solve this particular problem? Our interest, of course, is in this 1 kilohertz speech signal, low frequency speech signal. So that's where our general problem solving methodology comes in. We said this is the domain in which you want to solve a problem, and it's hard to solve the problem in this domain, while in this domain the problem is easier to solve. And so what we do is we transform the original problem into a problem in this particular domain, solve it here, and then transform it back. So the idea is the same. Why don't we apply this particular problem solving methodology to transmission of speech through wireless means? So how do we do that? Well, we take our speech signal, the sinusoid 2 pi into 10 power 3t here, and we use this transformation that we are talking about. We use the concept of modulation. So what we do is we take this particular signal and we modulate, let's say, the amplitude of this signal, high frequency signal, which is easy to wirelessly transmitted. We modulate the amplitude of that particular signal. So normal amplitude is Ym, but we modulated the amplitude with this particular signal here. So in effect, what we are saying is that we are sort of taking this particular signal and making it ride on top of this particular signal here, the signal, high frequency signal here. So note that to produce a signal like this, if you look at it, is nothing but the original signal Ym sine omega t plus a multiplication of xt and yt here. So all I need is a multiplier to enable to generate a signal like this. Now this is a high frequency signal here. So what we do is we transmit this signal, high frequency signal A to B, and this modulated signal here. And then once I reach B, I do a demodulation. In the sense, I do a demodulation and I extract my signal xt back from here. Okay, so demodulation, we'll see later on that we can do demodulation by a simple diode rectifier. If I have a rectifier with a resistor and a capacitor, the demodulation is fairly simple, and we can extract the signal back xt that you see here. Right, so we see the concept of modulation, and we see the concept of demodulation, and we see a general problem solving methodology that you see over here. Right, so this enables us to wirelessly transmit a low frequency speech signal over long distances by employing a high frequency signal, which is a carrier wave here. So it carries the low frequency speech signal on top of it here, right? So in this amplitude, the low frequency signal is embedded, and we're able to do that. So that brings us, so this is what we're talking about, radio. And this 450 kilohertz is AM radio, and we are talking about medium wave transmission. So 450 to about 1600 kilohertz is the medium wave band. And so we know that it's not just, let's say we're talking about news or music or whatever. So we have various different channels that we want to transmit. So typically what happens is then the different radio channels are separated by very narrow frequency interval. So for example, there may be one channel whose carrier frequency is 450 kilohertz. And there may be another channel at a carrier frequency of 460 or another at lower at 440. And obviously you want to receive the 450 kilohertz channel, let's say, and thereby you want to reject 460 or 440 kilohertz. So basically in terms of, we are talking in terms of filtering. You want to accept this particular signal, pass this particular signal, and reject both a higher signal and a lower signal. So you're looking at a band pass filter kind of a thing. And let's say this is 450 kilohertz, which you want to pass. And 460 kilohertz is, let's say, somewhere over here, and you want to reject it. Just for the sake of discussion, let us say that this is 0 dB, and we want to attenuate the 460 kilohertz by a factor of 10. And by a factor of 10, so this has to be 20 dBs below it, right? So factor of 10 attenuation. So thereby we will accept, our circuit will take this particular signal and then demodulate it, and we'll receive the speech or audio signal that is embedded in it, while this particular channel is getting rejected. So this will, it will not be received. So what kind of a filter are we looking at? So we have 450 kilohertz here and 0 dB, and at 460 kilohertz we have a 20 dB attenuation. So how many decades are there between 450 and 460? So we take log 10 of 460 by 450. So there are 10 per minus 2 decades there, right? So hardly a decade, but so what kind of an attenuation? We want to describe attenuation, if you recall, in filters in terms of how many dBs per decade. So that's why we are calculating. So we have these two frequencies here, and the number of decays is here. So in terms of dBs per decade, we are looking for an attenuation of 20 dBs over 9.5 into 10 per minus 3. So almost like 2000 dBs per decade. So we are looking at a very, very high attenuation, right? 2000 dBs per decade here. So how do we obtain such a high attenuation? Well, to see the difficulty of obtaining such a high attenuation, let's look at, so we had seen all these different filter types. And so we had seen this very simple filter, RC filter, a low pass filter. And we had seen that this RC filter provides us with the 20 dB per decade here. So note that the value here is minus 20, the value here is minus 40, and the change in frequency is 1 decade here. So 20 dBs per decade, right? And what was our target? We were looking at 2000 dBs per decade. So one simple RC filter only gives you 20 dB per decade. If I add 3 RC, so one of them, the idea is one of them will give 20 dB per decade, another one of them 20 dB per decade, and another one of them 20 dB per decade. And indeed this happens here. So what we find is that we are able to get, note here is minus 60 and then here is minus 120. So you're able to get 60 dB per decade. Now if we follow this kind of a line of thought, then 2000 dB per decade, you can imagine how many sections you will require. And thereby the circuit is going to become fairly complex. And that is where, so we would require recall that this is a first order transfer function, first order filter. This transfer function will have, this is a third order transfer function, in the sense that if we look at in the denominator, if we look at the highest power of omega, we will get a 3 here, and the highest power of omega will get 1 here. So as an example, we had seen this. This is a note that 1 plus j omega and 1 plus j omega, we multiply them together, we'll get an omega square in the denominator. It's a second order system, second order filter. And a second order filter will give you, we had seen this example here, gives you 40 dB per decade. We had also seen a case of third order system. If you multiply them all together, the highest power that you will get is omega to the power 3. It's a third order system, third order filter, and the maximum attenuation that you're able to get is 60 dB per decade. And so that is where, so if you have to build a 2000 dB per decade, this kind of an approach is not going to work, or the circuit will become too complex to obtain that kind of a attenuation or that kind of selectivity. So that's where the concept of resonance comes into picture. LCR circuits with resonance enable us to solve this problem of obtaining high selectivity with a very simple circuit. So resonance is a phenomena that is found in all kinds of systems, mechanical systems, atomic systems, molecules have resonance frequency, atoms have resonance frequency. And in our context, we're talking about a resonance in an electrical circuit. So the idea is that a circuit like this has a natural frequency, in the sense that if you disturb it, so here in this particular case, what we did was, if you look at Vs, we applied a sharp impulse, a very narrow pulse here, sharp impulse we applied. So the signal is applied momentarily and removed, right? A sharp impulse here. And what happens is we are looking at the output voltage. Note that the output breaks into an oscillation. The system starts oscillating, and after a while the system goes back to its equilibrium state here. So the system has a natural frequency, right? And depending on the value of L and C, we'll get different natural frequencies. Now, resonance, comes into, the concept of resonance comes into picture. So suppose I apply not just one pulse here, but I apply a train of pulses, right? So I apply a train of pulses here. So what happens is, we are expecting the system to, in the previous case, the oscillations were dying down. Now we are applying a train of pulses. So we are expecting the system to remain in an oscillatory state. And the system does remain in an oscillatory state. But, the amplitudes are small. The amplitude is small. And because we have applied a signal with a frequency which does not match the frequency of the natural frequency of the system. So note the amplitude is only 50 millivolt here. Well, similarly, for example, t is equal to 1.1 microsecond, the spacing of the impulses, the train of impulses that are there is 1.1 microsecond. Similarly, if I apply a little faster impulse, let's say 0.9 microsecond, again, the system is oscillating, but the amplitudes are relatively small, 50 millisecond. Now, if I match the frequency of this impulse, this input here, to the natural frequency of the system, then note what happens here. So in this case, the impulse frequency, the input is the rate at which I'm applying my input, or the input frequency, matches the natural frequency here. And note that the magnitude now reaches 500 millivolt here. 500 millivolt, about 10 times higher. And if I had a circuit with with less dissipation in it, with less resistors in it, this would have reached even higher. And so what we are talking about is that the systems have many of the systems have a natural frequency, and if you applied an input which matches the natural frequency, then you get the system responds with very high amplitude. And this is what we are finding. The system responds with a very high amplitude, and the moment so it responds with a very high amplitude, 500 millivolts. The moment you go away from the natural frequency, maybe a little higher than natural frequency or a little lower than natural frequency, the system does not respond very well, and the amplitude of the output of the system is fairly small here. So this is the concept that we want to utilize for obtaining very high selectivity. Use the concept of resonance. The signal that you want to capture or you want to pass, let that signal match the resonant frequency of the circuit, and the rest of the signals will be out of resonance with the circuit and will get naturally attenuated and rejected. So let me show an example here. So the simple circuit that we were talking about, L, C, and R, and this is the response, the output voltage versus frequency response of this particular circuit. And here the circuit has been designed, LC circuit has been designed such that the resonant frequency is 450 kilohertz, the signal that we want to pass. And note that the value here is 0 dB. And a little bit away from here, 460 kilohertz, the value, the attenuation is minus 24 dB. So note that we are able to obtain that very high attenuation that we were looking at, 2000 dBs per decade kind of an attenuation, using a very simple circuit with only an L and a C and an R, right? And very simple circuit, we are able to obtain very, very high selectivity. And the reason we are able to do it is because the circuit is based on the concept of resonance. The circuit has a natural frequency, and if the input matches the natural frequency, then the output responds very well, while anything which is away from the natural frequency, the system doesn't respond. System responds with a very low amplitude, right? So if we want to obtain a radio channel at 450 kilohertz and want to reject the radio channel at 460 kilohertz, this kind of an LC circuit is a right solution, and these are very commonly used in radio receivers. The series LCR circuit also has a similar behavior here. So if I use an L, C, and an R here, that also shows me the same kind of a behavior here. If I look at V out, very high kind of a selectivity we can obtain through that. So let's look at these LCR filters. So these are, this is nothing but a band pass filter. It will pass a very narrow band of frequencies around 450 kilohertz and rejects everything around it. All the lower frequencies and higher frequencies, they're all rejected. So it acts like a very nice band pass filter, very narrow band pass filter. All right, so let's look at these resonance circuits, series LCR, series resonance circuits, and parallel resonance circuits in a little bit more detail here. So, so what is really happening is that, okay, so let's go forward. So we have RLC here, and let's look at the amplitude of the impedance of this particular system here. So that's R plus j omega L minus j 1 over omega C. And so the current that you see here, the current would reach its maximum. The current would reach its maximum, and thereby the voltage drop across R would reach its maximum when the imaginary part here cancels out, and then you will obtain the impedance which is minimum, and thereby the current will reach its maximum value here. So that is the point of resonant frequency point. So we equate the imaginary part to be equal to 0, and we get a resonant frequency of omega naught equal to 1 over root LC and frequency of 1 over 2 pi square root LC. The net impedance in the circuit is simply R. The current and the voltage are in phase with each other, meaning that the power factor is unity. And so this is the condition under which so if you apply a frequency equal to F naught, the resonant frequency here, current magnitude of the current would be maximum, and power factor, or the angle between the voltage and the current, will be 0. Power factor will be unity. And so let's look at, let's examine the role of R, role of L and C in a little bit more detail here. So in general, we can do a phasor analysis and write down the magnitude of current in this particular manner here. And if we plot it out, we will see a behavior like this here. So in this case, the current is normalized by the maximum value of current that we will obtain, Vm by R, when omega L equal to 1 by omega C. This term goes to 0. So the maximum current is Vm by R. So we have normalized the current by Vm by R. And so the maximum value is 1. And then away from the resonant frequency, the current magnitude of the current falls on both sides here. And let's look at a point which is where the current falls to 1 over root 2. Current falls 1 over root 2 here and 1 over root 2. 1 over root 2 is 0.707. The reason 1 over root 2 is because then power is square of the current. Power is square of the current, and therefore these are also called half power frequencies. Half power frequency. So if we look at the power, let's say dissipated in resistor R, if power is let's say 100% here, then power at these particular points would be 50% here and 50% here, because the magnitude of the current falls to 1 over root 2 and power falls to half of that. So omega 1 and omega 2, the reason why we are looking at is we are saying that this is a band pass filter, and effectively we are saying that my filter is passing frequencies between omega 2 and omega 1. So this is like the bandwidth of the filter here. Omega 2 minus omega 1 is the bandwidth, and omega naught is the center frequency of my band pass filter. So those frequencies we can easily obtain by plugging it into this formula here, I omega 1, and by writing the amplitude as Vm by R, 1 over root 2 of that. So, we'll get I omega 1, and similarly we'll get I omega 2, both of these values. So we can obtain, by solving these equations, we can obtain an expression for omega 1, and we can obtain an expression for omega 2, these two frequencies that are there in the neighborhood of the center frequency that is there here. Right, so these are omega 1 and omega 2. And one can easily show that omega naught is, if you multiply them together, is nothing but geometric mean of omega 1 and omega 2. And the bandwidth we said is the difference between omega 2 and omega 1. So if we take the difference here, we'll get R by L. And we can define how sharp is my band pass filter, or how sharp is the resonance. We are saying that this kind of a characteristics is coming because of the phenomena of resonance here. So how sharp is it? Well, we can define sharpness in terms of the center frequency, omega naught divided by the bandwidth here, omega naught by delta omega. And if we substitute the expression for delta omega, which is R by L, so we obtain Q equal to omega naught L by R here, which we had seen in other contexts also, that series resonance circuits have a quality factor, or in this case sharpness of resonance, which is given by omega naught L by R. And although this is not of direct interest to us, you would see that Q factor is also described in terms of the energy, peak stored energy, either in the capacitor or the inductor, divided by the energy dissipated in one period at resonance here. So this is like the reactive power and the power which is dissipated in the resistor here. And the ratio of these two is the quality factor here. So if you want high quality factor, you should have a small value of R, so that less energy is dissipated in the resistor. And you should have high value of L, and so that you obtain a large energy stored in the inductor there. Right. Okay, so, and of course you can also express it Q as, using the relationship, you can express Q equal to 1 by omega naught C times R. So in this case, according to this expression also, you can see that you want a small value of resistor here. So resistor needs to be small in order to obtain large value of Q. And of course omega naught L, the reactance should be large here. This is the reactance of the inductor, and 1 over omega naught C is the reactance of the capacitor here. So the reactance have to be much larger than the resistors in the circuit here. And so that is kind of an obvious. This is the reactance part and this is the resistor part. That's kind of an obvious. So let's say R is 0.1 K, and let's say at a frequency below resonant frequency, this is J0.9 K, and let's say this is minus J1.1 K. Right, so what would be the net impedance in the circuit? And the net impedance will control the magnitude of the current. So the net impedance would be 0.1, and J0.9 K and minus J1.1 K will partly cancel each other, and you'll get minus 0.1 K. So if you take the impedance, magnitude of the impedance is around 0.1 K, right? It's related to of that particular order. On the other hand, let's say the reactants were higher. Reactances were higher. So let's say, oh, by the way, so this is away from the resonance. This is away from the resonance. And at resonance, what will happen is, as you increase the frequency, this will increase and this will decrease, and they cancel each other out, and the impedance will be 0.1 K. So if you compare the two, away from resonance, the impedance is higher than 0.1 K, but not by a large amount, right? It would be 0.1 square plus 0.1 square, and square root 2 times 0.1 K, and here is only 0.1 K, right? So there's not such a large change in impedance. And why is that happening? Because the reactive part of the circuit, the reactive impedance, is not that high compared to the resistive impedance here. 0.9K divided by 0.1K, or 1K if you look at it at resonance, 1K divided by 0.1K. It's only a factor of 10. On the other hand, if we look at the same thing, let's say this is 0.1K and this is 0.9 meg and 1.1 meg. So this is a little bit below resonance here. So the net impedance would be 0.1K minus J, 0.1 meg here. And if we take its magnitude, you can calculate what the magnitude is. So it would be around 0.1 meg here. Now at resonance, what will happen is as you increase the frequency, so this will become 1 meg and this will also become minus 1 meg here, right? So this will become here. These two will cancel each other. And so Z will become 0.1K. So now as you go from a little bit at a frequency a little bit below the resonant frequency to resonant frequency, the change in impedance that you get is from 0.1 meg, which is 10 to the power 5, to 0.1K, which is 10 to the power 2. Right, so you get a huge change in impedance. And thereby you will get a very sharp resonance. Huge change in impedance, which means there's a very large change in the current flowing in this condition versus this condition. And what is the reason for it? The reason is that the reactive impedance, whether you look at the impedance here or the impedance here, is much higher than the resistive part here. So that's what we are saying is basically the Q factor here. The reactive part is much larger than the resistive part here, and the reactive part is 1 by omega naught C is much larger than the resistive part here. So that's the condition that you require to obtain a very sharp resonance and high selectivity. Okay, so these are summary of what quality factor is and what the implications of high values of Q are. Right, so Q equal to omega naught L by R. Q is also omega naught by del omega, the bandwidth here. And you can show that if the Q value is high, then omega 1 is basically omega naught minus bandwidth by 2. Omega 2 is approximately omega naught plus bandwidth by 2 here. All right, so these are useful relations to remember. Relations of Q here. Bandwidth is basically R by L here, and Q another expression for Q, and omega 1 and omega 2. Okay, so we had seen earlier that these are 4 classes of filters. Here is a low pass filter, high pass filter, band pass filter, and band stop filter. So we have seen that these RLC circuits can provide us with very high selectivity, with very sharp attenuation away from the resonant frequency here. So in this case, if we look at this circuit here is, if we take the voltage across the capacitor, you can verify that this acts like a low pass filter. It passes the lower frequency and then higher frequencies it rejects, and interesting things happen around the resonant frequency part here. On the other hand, if I take the voltage across the inductor, then it looks like a high pass filter, right? So the same circuit that you see here, I can build a high pass filter kind of a thing. I can build a low pass filter, and if I take it across R, this we've already seen is a band pass filter here. And if we take L and C here together and take the output here, then note that at resonance, the L and C cancel each other. So this practically becomes short, and therefore it acts like a band stop filter. So if there is a frequency which you are interested in rejecting, now what happens is many times when we are building circuits, the circuit is of course powered with a power supply, and power supply, the DC voltage, let's say in the power supply, is obtained from the AC, which is a 50 Hertz signal. And despite the best efforts, sometimes some little bit of AC voltage may remain in the circuit, in the power supply, and that AC signal can get into your circuit, and you're interested of course in removing it. So then what you could do is you could pass your signal through a a band stop filter which is at 50 Hertz, and thereby you can reject any 50 Hertz signal that gets through, is rejected, and everything else is then passed around. Okay, so coming back to our problem of radio channels, we wanted to receive 450 kilohertz, but we wanted to reject 460 kilohertz by 20 dB here. And so this is the transfer function, and we are using the LCR circuit as a band pass filter here. And so basically, let's say the input is 1 volt, Q is omega naught L by R, we have seen here. And in terms of Q, we can write this circuit in this particular form here. Okay, V naught is 1 by square root, basically using the definition of Q, and using also the definition of omega naught is 1 by square root LC here. And so for omega equal to omega naught, if we plug in here, we'll see that V naught is 1, so the signal simply passed through. So that's fine. Omega naught is here. Now for if because we'll have very high selectivity to reject the 460 kilohertz signal here. So very high selectivity, which means that this factor would be much larger than 1, so we can ignore 1 here and simplify it to this kind here. And we can make a further simplification because the signal that we are rejecting, let's say omega 1, is very close to omega. We can further simplify it like this here. And so for an attenuation of minus 20 dB at omega minus omega naught. So we are rejecting basically 460 kilohertz signal. So 460 kilohertz minus 450 kilohertz multiplied by 2 pi is 62.8 here. And so if we plug in here the values of omega naught and omega minus omega naught here, we'll find that we require a Q of 226.3 here to be able to reject that 460 kilohertz signal here. So Q equal to 226.3 at 460 kilohertz. Q is omega naught L by R. So suppose we choose L equal to 1 millihenry, and then once you choose 1 millihenry here, L, and then we know the value of Q, and we know the value of omega naught, which is 450 kilohertz. So we'll obtain the value of R, and from omega naught, once you know L, you also know C here. So you obtain a design of a LCR circuit which will be able to pass 450 kilohertz and reject 460 kilohertz. And with a very high Q, of course, you require a very high Q of 226.3 here. Now there are applications where you want you're not happy with minus 20 dB, you want maybe minus 40 dB or minus 60 dB attenuation, and so therefore even higher values of Q would be required in those cases. You may require Q of maybe 10 to the power 4 or even higher. Okay, so let's come to the complementary circuit, which is the parallel resonance circuit. The previous one was series resonance, so L, C, and R, and in this case, for convenience, we are exciting it with the sinusoidal current, and we're looking at under what condition will the voltage across it be maximum. Right, so voltage across it will be maximum here, and so even if you have like this, you can, as you can obviously see, the voltage source and the resistor can be transformed into current source in parallel with the resistor. So both are equivalent in that form. So we want basically the voltage across this particular element to be maximum, and the voltage and the current to be in phase to get a power factor of unity here, right? So we can write the admittance of this particular part, 1 over R, these are in parallel, 1 over R, J omega C, and it will be 1 over J omega L, which becomes minus J here. And we note that the current, the impedance of this will be maximum, or the admittance of this will be minimum when I make the imaginary part equal to 0 here, right? So that's the resonant frequency for us. We make the imaginary part 0, so again the resonant frequency 1 over root LC, and then the admittance becomes 1 over R, and the output then is simply I naught times basically R here. Okay, so the net impedance is simply R here. All right, and in a similar manner we can find out the frequencies, half power frequencies here, the frequency at which let's say the amplitude of the voltage is 1 over root 2 here and 1 over root 2 here. So exactly same things we can repeat here, and we'll obtain two frequencies, omega 1 and omega 2. The bandwidth is omega 2 minus omega 1. Q factor can be written as omega naught RC or can be written as omega naught by the bandwidth here. And the important thing to note here is that Q is, just like in the previous lectures we had seen in this parallel LCR circuit, Q is R by omega naught L. Okay, R by omega naught L. And so in this case, you want very high values of R. So you want very, very high values of R compared to the reactance that is there. So a small reactance due to L and a small reactance due to capacitance and a high value of R will give you a high Q and a high selectivity circuit that is there. So these are basically complementary to what we've already discussed. So we'll skip some of these things here. So this is the case where you have a high Q circuit, then omega 1 and omega 2 can be very simply. So Q at least, high Q means at least Q greater than 10, then these approximations are fairly reasonable. Otherwise, you'll have to calculate using the full expression here, omega 1 and omega 2. Okay, so why is Q inverse of the series resonance? Why is it not omega L by R and why is it R by omega L? Well, that should be sort of, again, because note that at resonance we are trying to maximize the output voltage here. And again, same kind of an argument we can see here. So if it is 100K and this is minus J11 and J9, let's say just before resonance at omega 1, let's say this is the kind of a situation here. So this is together. They will have an impedance of J9 and J11, so you can calculate what the impedance will be here. And at resonance, and at resonance, of course, the two of them will exactly cancel each other, so you'll simply get 100K, right? So you look at what happens below resonance, a little bit below resonance here, where the impedance due to the inductor is a little bit lower than the impedance due to the capacitor here. So let's say this is J9K and minus J11K here. And and this is R here, right? So the basically the reactance that you see here, the reactance is 10K and this resistor is 100K. While in the next case, the reactance is still around 10K at resonance, but the resistance has been raised to 1000K, and you can see the difference between these two cases. Just a little bit below resonance, and as you go to resonance, what happens to the change in the impedance here? And I would suggest you look at the same thing in this particular case, and then you will realize why Q is R by omega L and not omega L by R in this particular case here. Okay. Now, so resonant frequency is very important for us, and if you're trying to pass a 450 kilohertz signal and you've designed an L and a C such that it's tuned to 450 kilohertz, you want to catch this particular radio channel. The problem is that L and C, if I take typical inductors and capacitors, they have problems of tolerance. So you may pick a capacitor which is labeled as 12.5 picofarad, but then when you exactly measure it, you'll find that the capacitor is not 12.5 picofarad, but because of tolerances, it's maybe 10%, 20% higher. Now 10%, you can do the calculation for these values. Let's say the center frequency is 450 kilohertz, and imagine the capacitor is 10% higher. Now 10% higher, which means that the frequency will not be 450 kilohertz, you'll go a little lower than 450 kilohertz, and therefore the circuit will not be tuned to 450 kilohertz. The circuit will have a resonant frequency which is lower than 450 kilohertz. So instead of catching 450 kilohertz radio station, you'll be actually rejecting it. And there's not only the problem of resonance, the problem of tolerance, there's also a problem of temperature causing changes in the values of the capacitor. So you may switch on your radio and the capacitor may have a value, let's say 12.5 picofarad, and inductor may have 10 millihenries. But then if you leave it for a while, as you operate, the circuits heat up, there's power dissipation, and the capacitor value may change. So one uses special capacitors. So for example, you can see here, these are capacitors which are called NP0. So they are temperature compensating capacitors here. So the capacitors and inductors have to be as much as possible independent of temperature. But despite taking all possible precautions, you can see here the percentage change in capacitance as a function of temperature. So these are very special capacitors, temperature compensating capacitors. But even here, you can see that the change in capacitance as you go to higher temperatures or lower temperatures, the change in capacitance is occurring 2-3% at least. And this 2-3% even change in capacitance may not be acceptable to you. Okay, this is the other thing that it is showing here, is showing that no matter which component you pick up, it's never a perfect, there's nothing called an ideal resistor, ideal capacitor, or an ideal inductor. So in this case, if you pick up a capacitor and you measure its impedance as a function of frequency, you should get a straight line. This is a log-log plot. Log-log plot. So if you plot log of impedance versus log of frequency, you should get a straight line. You do get it. It acts like ideal over this range, but note that here is where there's a shift here. It's no longer capacitive, but is becoming, at this point, the impedance is actually falling to 0 and then becoming inductive here. And here also is going from capacitive to inductive. So all capacitors have leads, and leads have inductors associated with them. They have some resistors associated with them. So at some higher frequencies, note that at some higher frequencies, omega L, the little bit of inductance which is there in your capacitance leads, that starts to become important, and you start getting distortion here. So all of your components, whether you pick up a resistor or a capacitor or an inductor, they would fail at certain frequencies. They would not act like the inductance that you want or the capacitance that you want. So coming back to a point, the point is that these capacitors and inductors, they have a temperature coefficient, they have a tolerance, and therefore, even though ideally you may be able to build a circuit which is tuned at 450 kilohertz, when you practically make it, because of these tolerances and because of drift due to temperature, you find that it's not tuned to 450 kilohertz. And so as I'm saying, you may start off and you may switch on your radio and it's tuned to 450 kilohertz, and then after a while, as your radio heats up, you find that the signal fades away, and then you may have to, in olden days especially, one would fiddle around with the inductor or a capacitor, variable inductance and a capacitor, and you will have to retune the circuit. And so that is a problem, especially if you have a high Q circuit here. A little bit of detuning of the circuit will cause a huge change in the output here. And in that context, this particular device becomes very interesting. So this is a piezoelectric quartz crystal. So it's basically a crystal of quartz with the contacts made at the two ends of the quartz crystal. And quartz has an interesting property called piezoelectricity. That is, if you apply pressure, then charges develop on the opposite side here. And the interesting thing about a quartz is that you can model it with this kind of an LCR circuit. So equivalent circuit of a quartz crystal with electrodes on two sides is an LCR, series LCR, and with a parallel capacitance also here. And so if we plot the impedance here, we'll see that impedance, basically it acts like a capacitive here. And then as you raise the value of the frequency, it is dominated here. This part becomes inductive here. This part becomes inductive. And very quickly then resonance occurs between these two. And then again, this part begins to dominate, and you get here. Okay, you get the circuit again becomes capacitive. So the idea is that this particular circuit is inductive over a very, very narrow frequency range here. Okay, extremely narrow range is inductive here. And these frequencies are extremely stable. And so one can build oscillators using this particular circuit with very, very high stability and very high reproducibility. Okay. And so let me show you. And the sharpness here that you see here, the sharpness is extremely high. And you can get Q of the order of 10 to the power 4 or 10 to the power 6. Very high Q circuits, very stable. frequency points here. FP is a very stable point here, and the stability with respect to both tolerance as well as temperature. So let me show you an example of a quartz crystal here, and note that the frequency tolerance at 25 degrees 50 parts per million, and the stability over the temperature range from minus 55 to 125 degrees is 50 parts per million here. So very stable. It provides you with a very stable resonant frequency here at this particular point here. So quartz, if you want a very high Q LCR circuit, very stable with very good tolerance, then quartz crystal itself is very good option, and is used in a wide variety of oscillator circuits here. Okay. And coming back to resonant frequency, so we've been using the word of resonant frequency, and if we take a circuit like this here, LC circuit like this with some resistor connected in parallel, we have been saying that resonant frequency is 1 by 2 pi square root LC. And if we plot the voltage output, we'll see that the voltage reaches a peak at the resonant frequency here. The voltage reaches a peak at the resonant frequency. Not only that, we have been also saying that at this value, the reactance due to the inductance is equal, but opposite in sign to the reactance due to the capacitance here. And so the two of them cancel each other here. And effectively, when they cancel each other, L and C act like open circuit here. And then you are left with only resistance in the circuit, and thereby the current and the voltage are in phase. So at resonance we also get zero phase here. So here we are plotting the phase part as a function of frequency, and you can see that the resonant frequency is 0.355 hertz, very low resonant frequency because of the choice that you see here, a large value of inductance and very large value of capacitance here. So in resonant frequency is very small, 0.355 hertz here. So at the frequency at which phase is zero, which means power factor is unity, voltage that developed here and the current are in phase with each other. So cos of phi is equal to 1, unity power factor here. So at the frequency at which power factor is 1, at the same frequency, the current reaches its maximum value here. So there is no ambiguity in saying what is the resonant frequency. And the power factor equal to unity means that the imaginary part of the impedance or admittance is they cancel each other, and you're left with only the resistor part here. But this is not really true if you have a little bit more complicated circuit here. So in this case, we have an L and a C, and note that we could have put this R also, but just for the sake of discussion, this R is not there. So we've added an R in series with L. So in this case, we would like to know what is the unity power factor. What is the frequency at which the current and the voltage that is developed are in phase with each other here. And so we are asking for that particular frequency. So we can write down, because it's parallel, it's easier to write down admittance here. So admittance due to the capacitance, and this particular branch is nothing but 1 plus 2 plus J2 omega here. And for zero power, not zero, but for zero phase difference or unity power factor here, imaginary part equal to 0. And so we can rewrite this in this particular form, and we can make imaginary part equal to 0, and we get omega not equal to 2 radian per second here. So we can say that the frequency at which the imaginary part of the impedance goes to 0, the circuit acts purely resistive with the unity power factor, and so that is my resonant frequency. And 2 radian per second translates into so this is nothing but the phase part here, and phase goes to 0 at 0.318 hertz or 318 millihertz, which is nothing but omega naught here. But if we look at the magnitude of the output voltage, so this is the phase part here, where the imaginary component goes to 0. The circuit is purely resistive at that frequency. If we look at the magnitude part here, the magnitude of the voltage here, the magnitude of the voltage goes to peak value not at zero phase here, 318 millihertz, but at 353.671. Right, so the two frequencies do not coincide. The frequency at which the phase goes to zero, or we have unity power factor, is not the same at which the output amplitude, let's say amplitude of the output voltage, reaches its maximum value here. So the two are not the same, right? So many times when we will refer to the resonant frequency, we'll say it is the unity power factor, where the phase angle between the current and the voltage is zero here, or zero phase frequency here. But it need not coincide with the part where the amplitude reaches its maximum. Okay, so that's while in the simple case when we had a pure LC circuit here with no R here, so the two of them would were coinciding with each other here at the same place where the phase goes to zero, the same place where the amplitude also went to maximum value here. Now, if you have something like this and you would like to analyze it, of course you can analyze in the manner that we have discussed. You can also analyze by transforming this particular circuit into a more familiar circuit. So we have all the results for when we had an L and a C, but now we have L and an R in series here. So what we can do is we can take this particular part, its impedance, this particular branch impedance is RS plus j omega Ls, and we can transform it into a parallel equivalent circuit. Into a parallel equivalent circuit by writing Ys equal to 1 over Zs. So that's equal to Rs plus j omega Ls. And we can simplify it, and we can have a real part and an imaginary part. And the real part, we can write it as 1 over Rp. And the imaginary part, we can write it as 1 plus j omega Lp here. So what we are saying is the following. The same Rs and in combination with Ls here can be rewritten as Ys equal to 1 over Rp plus 1 over j omega Lp, which means that it can be written as this form here. 1 over Rp plus 1 over j omega Lp as a parallel combination. So the series combination of R and L can be transformed into a parallel combination of R and P, with Rp given by this expression here and with Lp given by this expression. Right, so now what will be the zero power factor frequency, or zero phase difference frequency, or unity power factor frequency would be the place where the reactance due to capacitance will cancel the reactance due to the inductance that is there. Okay, so that would be easy to calculate here once you do this kind of a transformation. Right, so the idea is, instead of doing all the analysis from the beginning, we said maybe try to reuse the results that were obtained earlier. So if you transform this circuit into this familiar circuit, then many of the results that you have derived can also be used. The only problem is that in the previous circuits Rp was a constant, but in this case Rp is a function of omega, and as you change omega, Rp is also changing here. Okay, so zero, so this is an error. Zero phase difference or unity power factor frequency will be omega PLP is 1 over omega PC here, and of course so these are there here. Now the issue is that yes, zero power factor occurs, or zero phase difference and unity power factor occurs when the two of them cancel each other here, right? The omega PLP is 1 over omega PC here, but this is not the frequency at which Y is minimum, because note that earlier when Rp was constant, then the moment you make this term equal to 0, Y becomes minimum, and Y becomes minimum, and therefore the impedance Z becomes maximum, and you would obtain the maximum output voltage here. But now Rp is also a function of frequency. In fact, Rp increases with frequency here. So what happens is that at the point where this cancels here, Rp has a certain value. Now if you go a little bit higher in frequency here, Rp becomes even higher here. This term may not be 0 now, but together the Y is still, if you take the magnitude of Y is still lower as compared to the case where this term was 0 here. And it's for that reason, that's a qualitative reason why we have to go a little bit beyond the zero phase part to obtain the place where Y reaches its minimum here, because Rp increases with omega here. So beyond this particular point, this term decreases. This term may increase a little bit, but overall, y reaches its minimum value at a different frequency as compared to this particular part here. Now, to calculate where does y reach its peak, of course, we have to take it and take its derivative, and it's a little bit more involved calculation to figure out the frequency at which omega at which the y reaches its minimum value here. So we know how to analyze this particular resonance circuit. So we can also have circuits like this here. We have L and a C and an R. And again, this does not fall into the results that we have discussed, but the C and R, series combination of C and R, you can transform it into a CP and an RP in parallel. Using the same approach that we used here, you could use the same approach here also, and thereby transform it into a completely parallel circuit. In this case, this looks like a series LCR circuit, but then we have a capacitor in parallel with a resistor. So in this case, you could take this particular element, this parallel combination is y equal to r plus j omega c. You can, using the same approach, transform it into a series combination of a resistor and a capacitor here. And the moment you do that, then it becomes a more familiar series LCR circuit, right? So basically y equal to r plus j omega c, you write z equal to 1 over y, rewrite it in this particular form, and then separate it out into a real part, imaginary part. And then because the real, you're writing it as Z, so you can write it in terms of some series resistance and series capacitance here. And if you're, in this case also, a parallel combination of L and R can be transformed into a series combination of L and R here. So any of these circuits, you could, by transforming, note that a series circuit can be transformed into parallel, a parallel circuit can be transformed into a series. And thereby you can obtain, use some of the results that we have derived earlier. Especially the zero phase or unity power factor frequencies they become easier to calculate because that's the place where the reactance or the imaginary terms, they go to zero. The reactances cancel each other and imaginary terms goes to zero here. So let's stop by saying that resonance, the concept of resonance, the phenomena of resonance allows us to build highly selective filters in a very efficient manner. Using only an L and a C and an R, we are able to get very, very high attenuation away from the resonant frequency. And if you're looking for very high Q, very high selective, quartz crystals provide you with very stable frequency and temperature insensitive with very good tolerance capabilities and with very high Q. All right, so let's stop here.